edge designations, CFA level 1, pre-reading, quantitative methods, learning module 2, organizing, visualizing, and describing data. We continue on. This is video number 2 of hopefully 2 videos, and we continue on with the next learning outcome statement: calculate and interpret measures of central tendency. We start off with a basic description of what is statistics. Okay, I'm not going to spend too much time here. We talk about descriptive statistics, okay, which in fact describes, look at the words descriptive statistics, okay, describes or tells us something about the data. We'll move on to where most of the the more useful, I suppose, statistics comes in, and that is called inferential statistics. Okay, over our page. And look at the word again, infer, that we draw conclusions about the data. So we can use the data to try and make inferences about the specific data. Just a lot of what we do over here, guys, you've just got to get a little bit used to in terms of the notations, how we write things and things like that. For example, over here, you've got populations and samples. Population, for example, whenever we deal with the size of a population or a sample, that's always denoted by an N, but for a whole population, we denote that by a big N, and for a sample, we denote that by a little n. Okay, and obviously the difference between a population and a sample, a population is the entire population, every single observation, okay, that is possible within that specific group that we are looking at. A sample says, hold on a second, I'm not able to get all of that data that is out there. I know it's all out there, I can't get it all, it's too expensive, we don't need it all for whatever reasons, and we're just going to pick a sample. Of course, remember guys, a sample comes from the population, we pick it out of the population. Some very important stuff, you're going to laugh, okay, the difference between a parameter, okay, what is a parameter? A parameter is there to describe something coming out of the population. Okay, what's the difference then between a parameter and a statistic? Only difference, guys, or for our purposes for now, a parameter relates to the population. Nice and easy to remember, P and P, and a statistic relates to a sample, again S and S, nice and easy. That's all. Okay, I wouldn't spend too much time worrying about that. We then move on to measures of central tendency. Important to remember that at this point in time there are 4 measures that we work with, or we call them sample moments. Okay, in this pre-read, we deal predominantly with 2. Number 1 being measures of central tendency, and number 2 will be measures of dispersion. There are other 2 as well, which is measures of leptokurtosis or kurtosis, okay, and then measures of skewness, both right and left skewness. But in this particular pre-read, we only deal with 2 measures of central tendency, number 1, and measures of dispersion. When talking about measures of central tendency or measures of location, okay, and look at the words, measures of central tendency, we start off with the mean being the average. Now, remember, if we have got a normal distribution, something looking like that, normal distribution means that it is normally distributed, and you almost hold yourself a mirror there in the middle. The left side would look exactly like the right side. Okay, that's a normal distribution. Mean is the average, the middle. Median is the middle number. We'll talk about how that differs from the mean. The mean is the average. The median is purely the middle number. The mode is the number that comes up the most amount of times, and we could have, depending on if it's only one, that would be unimodal. If a distribution's got 2 points, that both of them come up the same amount of times. Bimodal, bi meaning 2, trimodal meaning 3. Let's have a look at a quick example over here. Okay, and here's my distribution. That's the whole distribution. You can have big distributions, you can have small distributions. This particular distribution, and what I want to do first, just before we move on, and we'll see it later on as well, but what I always do whenever you get a distribution is let us order the distribution. When I say order the distribution, let's go in the order. So I'm going to start with the 3. I'm going to move on to the 4, 7, 7, and 9. Is everybody come? Now I've ordered my distribution. When I want to calculate the mean or the average, look what I do down here, guys. Okay, my numerator, I sum all the numbers together to total 30. Okay, and I divide that by the denominator. How many values are there? There's 5. Okay, and I get to a mean or an average of 6. A very important point I just want to mention over here, it makes no difference, guys, over here for means or for any measures of central tendency. My first big measure that I deal with makes no difference if I'm dealing with a population or I'm dealing with a sample, whatever that number is. Sample, we use big N. Sorry, population, we use big N. Sample, we use little n. I always use the exact number. And you'll see why I mention that here, because when we move to the second measure, measures of dispersion, when I'm dealing with a sample, I never use the actual little n. I always use n minus 1. We'll deal with that in a second. Okay, but just remember with means, measures of central tendency, whatever the population size is, whatever the sample size is, I use it as is without making any distinctions over there. Okay, and that's the mean, guys. A nice simple word for the mean, if you're looking for it, would just be the word, my apologies, the word would just be average. Is everybody comfortable with that? So nice and simple. What we're going to do as we go forward, guys, we're going to deal with different kinds of averages, different kinds of means, but essentially all that a mean means is it's an average. Okay, over the page over here, okay, we now move to the next thing, which is your median. Okay, and I just want to go back, sorry, one page back. I'll work with this example over here. Now, if I say to you, what is the median? Median is the middle number. So 1, 2, 3. We've got 5 numbers. What's the middle number? The third number, which is what, guys? It's a 7. My median in this particular example is 7. What's my mode? What number comes up the most amount of times? 7 as well. Everybody comfortable? It's as simple as that. And I wish I could make it more complicated. That is as simple as it gets. Okay, there's a few examples for you there. I'm not going to spend too much more time. I just want to show you one little example over here, an interesting one. Consider the following data, and this is my whole distribution: a 0, a 1, a 1, a 1, and a 997. Okay, well, how do we calculate the mean? We sum them all together. There's my numerator. My numerator equals to 1,000. My denominator, how many observations? There were 5. What's my mean? 200. Now, why is this a bit of a problem? Because now look what you've got. You've got an average of 200, whereas really it shouldn't be that. But you've got one massive number, which we're going to call an outlier, that causes a massive, what we call skewness, starts to skew the distribution. Okay, we don't deal with skewness much over here in the pre-read. We'll deal with it much more in the core readings. Okay, yeah, I'm not going to spend too much time. Just in terms of it, and again, this is not really too much for this particular pre-read. Let's have a quick look at it. Okay, what do you do with an outlier when you've got one extreme value like we've shown you over there? Well, you can use that. You can use it as it is. It is real, although yes, it distorts the data, but it is real, so you can use it as it is. We can say you can remove all the outliers. That's called a trimmed mean. Why? Because you just remove them, you trim them, you cut them away. Okay, and there's another one called a Windsorized or Windsorized mean. A Windsorized mean is you replace the outliers with other values. So, well, it's not likely to ever be a number as high as 997. Well, let's get rid of it, and we'll replace it with another number. Okay, everybody comfortable? and I'm not going to spend too much more time. As I said, there's sometimes we do go a little bit in detail in the notes, but they're all there for you. I'm going to turn a couple pages, okay, and to here, bottom of this page, if you are following on together with me, let me give you a page number. It's page 20. Okay, we spoke about the population and the samples. Population mean, it's denoted by the Greek letter mu. So if you ever see that, that means that you're trying to calculate the population mean, okay? And over here, guys, the sample mean is denoted by X bar. What's the difference in how we handle them? Nothing at all. Okay, so nothing to worry about there at all. Okay, and there's a nice little example of a sample mean for you. Do take a look at that. Remember what we spoke about earlier when we said that there are many different kinds of means. So what we've been dealing with up until now is a normal mean. By the way, it goes by the name, okay, arithmetic mean. Is everybody comfortable with that? Okay, we now deal with this concept called a weighted mean. Okay, and a weighted mean, why do we have a weighted mean? Why don't we just use the numbers as they are? And the reason for that is what we say is there are often times when some data, and presumably it's going to be the data that is more recent, and we say that the more recent data, okay, is more applicable to us and therefore deserves a higher weighting than perhaps older data. Have a look over here. A year ago, a certain share had a price of $6. And now remember, guys, that is my most recent. 6 months ago, the price was $6.20. Now it's trading at $7.50. Okay, I'm sorry, my apologies. I've said that exactly the wrong way around. Let's just do a redo. Okay, a year ago, that's the oldest. My apologies. The share price had a price of $6. 6 months ago, $6.20, and now it's trading at $7.50. $7.50 then, yes, is the most recent. The question then says to you, and obviously, guys, we always try and weight things based on the most recent observations. The question says to you, do me a favor, please weight in the ratios of 1 to 4, okay, such that the current share price is twice as important, and then the current price is 4 times as important as the price last year. Okay, what we do is we take our, and I'm just going to change my colors over here so we can see it nice and clearly. Okay, let's get rid of all of that. Okay, when we start off over here, and my first oldest price is $6, and that gets a ratio of 1, so we do 6 times 1. Next most important is $6.20. That gets a ratio of 2. Can everyone see how it goes? $6.20 times 2. And then my most important one is the $7.50, obviously because it's the most recent. It gets a weighting then of 4. So I go 4 times $7.50. So you can see what I've done, guys. Instead of just using a normal arithmetic mean, I sum them together after I've given them some kind of a weighting. Where do you get the weighting structure from? In most cases, the question will give it to you. So there's my numerator. I have now got 4840. My denominator, where do you get that from? Your denominator is always going to be whatever the ratios you dealt with. So it's 1 plus 2 plus 4, and that then will give me my denominator. Can anyone see over there? And now I get not an arithmetic mean, but a weighted mean. Okay, and of course, guys, you can just change the numbers around and as you see fit, of course. Okay, and there's another little example for you. Do take a look at that. I'm not going to spend time on that particular one. Okay, we move on over here, and I want to take you to the very next type of mean. Is everybody comfortable? We had to stop at this point. You could tell me that we have dealt with normal arithmetic means. We've also dealt with a weighted mean. We move to the third mean over here, which is probably one of the most used means, which is called a geometric mean. Okay, now some of the problems with an arithmetic mean, which we've been dealing with up until now, it does get badly affected by outliers. Okay, it cannot be determined if you don't know how many values in the data set. Okay, It takes all values from the data set into account. Nothing is left out. Okay. Often the value is unique. Okay. All interval and ratio data sets have got what we call an arithmetic mean. Okay. The sum of deviations will always take you straight back to the number 0. Okay, there we go. Now, let's go over the page, and then to calculate that's nice and simple. But let's now move on to geometric means. I think we've spoken enough about arithmetic means. Geometric means, okay, is often what we use when we're working with time series or return data. And look what we do. Let's have a look over here. Okay, suppose that a certain share returned values of 6.1% in 1 year, minus 2.8% in the next year, 7% in the third, and 4.9% in the fourth of the past 4 years. Now, if I wanted to calculate an arithmetic mean, I would sum those 4 together, divide by 4. Okay. Geometric mean, okay, look what we do. We take each and every one of those numbers and I root them. Okay, but before I take the actual number, what do I do with it? I'm going to go 1 plus, and how do we show 6.1%? Everyone comfortable? 0.061. So 1 plus 0.061. Is everyone comfortable? That's my first one. What's my next one? How do we show, it's going to be a minus 0.028. Everyone comfortable? So now I go over here, times, okay, and now we've got to go 1 plus minus 0.028. Everyone comfortable? Next one, and I'm just going to start to abbreviate a little bit over here. Is everybody comfortable? I would go over here, 1.07. That's 1 plus the 7%. And my last one would be 0.49, which I would go, let me make that a little bit bigger. Okay, I would go times 1.049. Is everybody comfortable what I've done? So remember, you take each and every one of the items, you add a 1 to it, okay, and you multiply them all out by each other. Step 1. Step 2 is you put that to the root of 4. Why to the root of 4? Because there are 4 observations. Everybody comfortable? But but remember, what have we done so far? Okay, in front of each of these items, we added a 1, didn't we? 1 plus 6.11. Don't forget at the end to do what, guys? Subtract a 1. Okay, and this is what we call the geometric mean, or geometric linking. And there's your 3.752%. Okay, so again, there's a 3-step process. You take each of your numbers, you add a 1 to it, you multiply them all out by each other, you root those to the root of however many observations there are here. It's to 4, there's to the root of 4. And don't forget, because you added 1 in the beginning, don't forget to minus 1 on the back end. Everybody comfortable? That's called geometric means. And just when you thought we were finished with means, we are not. Now we deal with harmonic means. Harmonic means is used to do some kind of what we call cost averaging. So for example, if you bought shares over the past period and you want to say, well, what's the average cost of those particular shares over the last period? The best way to do that is to use a harmonic mean. Okay, and interesting calculation I'm going to show it to you via example. Okay, an investor purchased stock in company A over the past 4 months. Here's his share prices. Okay, and what you do, you numerate. You say, well, there's how many months are we dealing with, or how many observations? 4. That's my numerator. And what's on my bottom? 1 over, what did he pay in the first month? 5. 1 over 5. Plus second month, 6. Plus 1 over 6. Next month, third month, paid 7. Plus 1 over 7. Okay, and the very last one is $8, so go 1 over 8. Run all your numbers, guys, and you get to, as we say, some kind of a cost average, $6.30, which is kind of like the average price over that. There we go. Now remember, as we come to the end over here, is everybody comfortable that we've got the different means? Let's just go through some of those quite quickly. Okay, number 1, we had arithmetic means. Then we took that arithmetic mean and we gave greater weightings to certain observations, and we called those the weighted means. We went from weighted means to geometric means, and from geometric means we went to harmonic means. Everybody comfortable? Okay. Top of page 26. Evaluate definitions of means to address an investment problem. Okay, so you need to look at the various components over here, guys. For example, okay, do we include all the values that we're going to, even if they are outliers and quite wild numbers? If we are, well, then you could just use the arithmetic mean. If you're going to make use of compounding, and like what we showed you before, you're trying to calculate a return over a long-term period, geometric means. Okay, and if there's some extreme outliers, what could you use? Remember we showed you this before. The trimmed mean. The trimmed mean is you just cut away the outlier, you get rid of it. Windsorized mean. Okay, we spoke about that a little bit earlier as well. Okay, you make an adjustment to that number, you don't use it as it is. And harmonic means we've discussed as well. That was that interesting calculation to give you some kind of a cost or some kind of a average. Okay, we are back with certain visualizations. We talk about quantiles, quartiles, deciles, all this kind of good stuff. And again, what I'm doing is I'm breaking the data down into certain more manageable groups. Quartile means I break it down into 4, so you can see there's the 25%, 75%. Okay, we've also got an interesting one called an interquartile range. They do like to work with us a little bit. Okay, the interquartile range. Okay, quarter 1 is, that's my 25%. Quarter 3 is 75%. The interquartile range will give you an indication of the spread of the middle 50% of the data, because it's between quarter 1 at 25 and quarter 3 at 75, so it's the middle 50% then of the data. Quintiles, quin is 5. Okay, we break the data into 5 equal parts. Decile is 10. Percentile is obviously, we know that, break it down into percent is 100%. Okay, and there we go. I'm not going to spend too much more there. If you do look over here, guys, we've got this interesting, okay, we're starting to talk a little bit about dispersion measures over here. It's called a box and whisker plot. Here it is. Why is it called a box and a whisker plot? Okay, it's got a box. Here's the box. What does the box represent, by the way? The interquartile range between quarter 1 at 25% and quarter 3 at 75%. So this, guys, would reflect, as we said, the 50% middle range. Okay, why is it called whiskers? Well, there are the whiskers. Those are what's connected to the box. Okay, and they are bounded by fences, a max fence and a minimum fence, which are the highest and lowest values of the distribution. Okay, and obviously anything there would be considered. Let's start to get the what we call outliers. Okay, everybody comfortable? Of our page, now we move, top of page 28, guys. Now we move to a different concept which we spoke about a little bit earlier. This is the second measure. Just to repeat, guys, the first measure was what we call measures, okay, of central tendency. Everybody comfortable with that? Measures of central tendency. This is the second one, okay, in the group of 4 measures of dispersion. Now, guys, look at the word. What does the word tell you? Measures of dispersion. Dispersion means how dispersed or how far apart things are. Just some important concepts over here with measures of dispersion. The minute you talk about this particular concept, guys, measures of dispersion, how far apart, how wide apart certain things are. An important thing is that of risk. Now, interesting, like, wow, how does risk fit in over here? Well, look at the dispersion. Now, remember, what is the very definition of risk? The definition of risk is that how far apart the actual outcome is, okay, from what? The expected outcome. Now, when we deal with expected outcomes or averages in quants, what's that called? The mean, the average. Now it also hopefully starts to fit in a little bit. So the minute you start to say, well, how far apart was my actual observation, in fact, what actually occurred relative to the mean or the average or to what was expected, that's called risk, by the way. That's a fancy term for risk, number one. Okay, and in terms of that, okay, what we call that particular risk, okay, is called standard deviation. Okay, we're gonna go talk about all those various concepts now. Okay, so dispersion is how far apart things are from. It's always got to be from something. So when we say how far apart is your actual observation from something, from what? From the mean. So can you see we only start to work with measure 2, measures of dispersion, after we've calculated the measure of central tendency, the mean, because there's an order to things. Okay, but we've got to compare one to the other. Measures of dispersion, let's have a look over here, guys. I've got the following portfolios over the past period: 10%, 30%, 5%, and 15%. Straight away, remember, guys, we always start off and say, well, what's the mean and what's the average? You sum those together, that's your numerator. Your denominator is how many observations were there? There were 4, and I get to a mean or an average of 15%. Now we start to calculate our various measures of dispersion. The very first one is called your range. Your range says, well, take your highest value and your lowest value. Highest value 30 from over there, lowest value 5, okay, and the difference between the two of them would be your range, how far apart they are, and that's obviously 25%. Nice and easy. Okay, we get our next one, which is called MAD. MAD, interesting term, okay, is mean, okay, but it's important over here, guys, when we talk about the word mean, okay, it's not the word, of course, is mean, absolute deviation. What does it mean? What's mean absolute deviation? Okay, mean absolute deviation is I'm working with absolute values. Okay, so let's just say, for example, my first one, remember, any kind of deviation that I'm working with over here, guys, is as follows. So remember, we've calculated our mean, our average at 15%. Let's go for my very first one. Let's go back for the data. The data was 10%, 30%, 5%, and 15%. So what's my first deviation? Let's draw ourselves a nice long line, not so straight there. What's my first deviation? It's going to be 10, which I've taken from here, less, what's my average? 15. Now what does 10 less 15 give you? Well, it gives you minus 5, doesn't it? But in this particular calculation for the mean absolute deviation, what do I use, guys? A plus 5. I'm using absolute numbers. And I go through them all. My second one, guys, is what? 30. 30 less 15 is my 15 over there. 5 less 15, not minus 10, which is the real answer, but plus 10, but we use absolute numbers. And then the last one, 15 less 15, of course, is equal to 0. Don't forget to divide by 4. Okay, there we go, 30 divided by 4. It's mean absolute deviation, and there's my number, 7.5%. Okay, everybody comfortable. So, and guys, just remember, whenever you get these particular signs, okay, 2 lines across like that, okay, 2 vertical lines, that obviously means whatever's in there is an absolute number. Doesn't matter if it's negative, we use it as it is. Okay. The next major measure of dispersion is called variance. Okay. And look at the variance calculation. We're going to go with our same data again, guys. Let me just reproduce it for you. 10, 30, 5, and 15. Look at my variance calculation. First, let's denote it as follows. Variance calculation as follows. Okay. Equal to, okay. Again, you do the same thing, but now it's not mean absolute, it's actual number. So I go 10. 10 I've taken from there. Remember, my mean or my average was 15, so it's 10 minus 15, which is minus 5. It doesn't matter because we square all of these. Let's go for the next one. Plus is my 30. Okay. Plus 30 less 15. Don't forget to square that one. Okay. Next one. Plus 5 less. Again, the same mean. Can I use the same mean all the time? Don't forget to square that one. And lastly, 15, which is this number there. There's the mean of 15, and don't forget to square that. So guys, at the end of it, of course, don't forget to divide by the number of observations. Over here, it is 4 observations. I come out with a variance, okay, of 87.5. Everybody comfortable how to get. So don't forget over here, everything is squared. Okay, why do we square everything? Of course, that will get rid of my negatives if they are there. Now, why do we move from variance, and how do we move from variance to standard deviation? Okay, variance is measured in units squared, not so convenient. To get a more standardized number, we use standard deviation. And the way, nice and simple, guys, to go from variance to standard deviation, all I do is I root the variance. So standard deviation is equal to the root of the variance. Everybody comfortable with that? Very fancy over there. Okay, over our page. And the last little bit I want to teach you over here, guys, is that we spoke about when we spoke about measures of central tendency, that there was no difference at all, guys, when I dealt with mu, which was the mean for the whole population, or x bar when I dealt with the mean for a sample. However, when we come over here and I'm dealing with the mean, so not the mean, the variance, standard deviation, doesn't matter which one, I'm just going to denote it by a big N, okay, it equals to the actual number, whatever the actual population is, for any measures of dispersion, they are what they are. As it shows you, so it is. Everybody comfortable? But for little n, when I'm dealing with a sample, I'm always going to go n minus 1. So remember, when I'm dealing with any kind of measure of dispersion, variance, standard deviation, anything over here, and I'm working with a sample, I'm always going to go, sample is always equal to, guys, as you know, little n, and that's equal to n minus 1. Everybody comfortable? And that's what we show. Don't go too much into detail. You don't really need to understand why. It removes the bias from the estimator. If that's things that are of interest to you, those are much more detailed statistical stuff. Come and join us in FRM. Okay, there we go. Can everyone see it? You can see over here. We're trying to remove the unbiased estimate, or the bias in the estimator. Okay, so just remember, guys, whenever you're dealing with measures of central tendency, okay, which is what we normally deal with for means and things like that, big N is equal to little n, and use the actual number. The minute I'm dealing with measures of dispersion, big N population, I use as is. Little n, which is a sample, I always go little n minus 1, always. And what if there's 100 items? We go n minus 1. What if there's 10 items? N minus 1. The 1 is always will be a constant over there. Got another interesting measure over here, which is called target downside deviation. What's target downside deviation? Standard deviation just does what, guys? Standard deviation just says, hold on a second. Remember, part of the standard deviation always starts off with variance, and at the end I root it. But what's the inherent calculation? That's the actual observation less a mean or an average, and we square that. This particular measure, called the semi-standard deviation, and just one point I want to mention, whenever you've got an actual observation, we call that XI. X, the observation, I, the specific one for that. Semi-standard deviation does exactly the same thing as a standard deviation calc. You can see over there, guys, it roots it. But what is it rooting now? Now look over here. It roots XI. That's exactly the same as what we saw before. In other words, it roots the actual observation, but now it's less, not the mean, less a whatever target you decide to set. Okay, we call that over here. Okay, and this measures, obviously, that target you'll set as some kind of a downside risk measure. You never want it to go below a certain value. Okay, and that's called target semi-deviation. And that's this formula over there. And again, you can, I will show you an example over here. Consider the following monthly returns. There we go. 6%, 4% in Feb, 0 in March, and -3 in April. And we've got a target return. You don't want it to go below 4%. Okay. Now when I'm calculating my semi-standard deviation, January and Feb, well, if I had to put in another column over here, which I would call target of 4% all the way down. In Jan and Feb, did I go below 4? No, I got 6 and I got 4. In March, can you see how much lower I am than my target? Okay. There's the 4% over there because I achieved 0. And in April, it's -3 is what I actually achieved. -4, which is in fact -7. You square the deviations as we always square them over there. You sum them together and you root them. Okay, everybody comfortable with that? Okay, so it's an interesting calculation, but it's one that takes into account, okay, the fact that what we're dealing over here with is amounts not different to a mean, but amounts different to a target. And of course, you can set that target to anything that you want. Is everybody comfortable with that? Okay, hopefully that makes a little bit of sense. Okay, let us get going over our page over here. Last little bit over here is what we call the coefficient of variation. What is a coefficient of variation? Another interesting term we've got over here, guys. And the coefficient of variation says, well, we want to make things comparable. And really, whenever you got the word coefficient is some kind of a standardization. Okay, coefficient of variation says, well, for anything that I've got, my coefficient of variation is the S, the risk, standard deviation over the return over the mean. What can I do now? Now I can compare two investments. What am I doing over here, guys? I'm saying, well, the risk is my numerator. In other words, how risky that particular investment is, over the mean, okay, which now I can say, oh, well, let's see that various mean, and let's just see if I can't compare units of risk per unit of return. Make it a little bit more comparable. Let's have a look at an example over here. Coefficient of variation. I've got the returns for a treasury bill, 0.23. Remember, a treasury bill is not so risky. There's the 0.3. So let's calculate its coefficient of variation. 0.3 is its return. Okay, sorry, my apologies. Let me just clean that up a bit. 0.3 is a standard deviation. That's its level of risk over its return of 0.3. How would we interpret this 1.304? We could say, well, that is the units of risk, 0.3 standard deviation for every unit of return. Not bad. Okay, a certain measure of risk. Okay, when I now move to small stocks, measure of risk is 7. That's massive, at least in comparable to the 0.3, and I'm getting a 1.4 return. So it's a much higher level of risk, okay, on a relative basis for small stocks, risk over return versus risk over return for treasury bills. But you can see what the coefficient of variation did for me is it made my numbers a little bit more comparable. That then, guys, brings us to a conclusion of learning module 2, organizing, visualizing, and describing data. On top of page 23, we give you a complete summary of the particular reading, just to make it a bit easier for you to go and have a look at. What you notice, I've also given you some over here as well. Okay, there's all your numbers for those that would like them. Okay, in a bit of a table form, and yeah, that is the total summary for you, guys. What I always like to do, okay, when I'm finished doing a particular learning module, is to go right back to the beginning. Okay, no one likes to go back to the beginning when you are finished, but it's quite important. Go back to the beginning, look at your learning module, learning outcome statements over here, and just say, for example, over here, interpret a contingency table. If you say to yourself at this point, a contingency table, I have no idea what that even is, perhaps you need to go look at that again. If you, on the other side, which I'm hoping the answer is, you say, contingency table, I know what that is. A contingency table is, okay. Everybody comfortable? Go through the learning objectives again. Make sure you're able to do them. Make sure you've taken out of the particular learning module what you need to. We will continue onwards with learning module number 3, probability concepts, coming up.